Right. So let's say we have a solid slab, like this. Maybe put it like this one, yeah. And then let's draw it. Okay. So let's say we have a solid slab. Slab is look like a long block like that. It's called slab. Maybe something like that. So this is slab. Okay. And then it's occupying space between y equal to minus b and y equal to plus b. So if you have, like, for example, this is the z and this is the y. So maybe in long plus b and minus b. So it's like long, that one. Okay. And then it's initially at temperature T0. So this one is in T0 at T0 at the time equal to 0. Okay. And then when T more than 0 at or equal to 0 and then start at T equal to 0, the surface of this one is suddenly heated into a T1. So it suddenly heated to T1. So like you suddenly expose the slab into maybe a hot temperature and maintain there. For example, if you have a slab, a slab of steel, for example, and then suddenly you put it into a furnace, and the furnace is hot, so you still have a remaining your initial temperature, of course, in the beginning, but from the outside you expose with a temperature of T1. Okay, so if we consider a dimensionless temperature at tau or theta, the theta always the delta T over delta T. So this is your sudden temperature, the temperature of your increasing, including the initial temperature, and this is the temperature, the increasing temperature, the sudden raise to your temperature. And then so this one, this T would be a function of, any idea? Would be, of course, a function of position. So it's a function of y for this case, and also a function of a temperature as well. Okay, so that's why, so for the dimensionless temperature, the tau, sorry, the theta, which is the dimensional temperature, would be then a function of the coordinate or the position in y. For y, the dimensional temperature is mu, and then for the dimensionless time, it we get a tau, which is tau is defined as alpha multiplied with the time divided by b squared. What is b? B is this one. It's the distance, the half thickness here. And then alpha, do you remember what is alpha? It's the heat diffusivity, or K divided by rho Cp. Yeah, so if you have the conductivity of your slab, of your steel slab, you know the rho, you know the density, and you know the heat capacity, then you can find the heat diffusivity, diffusive panas. Okay, and then you can get the thickness. Okay, and then if we substitute and then also solve the problems, it is not included in here, but then I think we can, yeah, if you want to try it using you know, the differentiation and so on, you end up with this one, with dou of the temperature divided by dou T, which is function of temperature, is the second differentiation of the temperature dimensionless divided by the coordinate. And this is the initial condition and also the boundary condition, where at the n plus n minus 1, over here, yeah, on the b and minus b, the theta is equal to 1. The theta equals to 0, which is t still exposed and the 0. Okay. Okay. Now here is the solution for heating a slab. So this is what it shows. So this graph, how to read this one. So this one is the dimensionless of the temperature. Your T minus T0 divided by T1 minus T0. So T is your temperature, which is you're looking for, which is a function of coordinate and time, coordinate and time, okay? And T0 is your initial temp, okay? And T1 is your exposed temperature, okay? And then if you look at here, there is a position as well, Y over B. So in when Y over B equal to 0, so that means if this is a slab, so in this in the center, so that means this would be in the center of the slab. If you have a slab, it would be in the center. This one, okay. This one, when Y over B equal to 1, so then you're either on the over there, or on the outside, so which is on the surface of the slab, okay. So then this is your theta, and then this is your this one, and the last one that's very important as well is this one. This is your alpha theta divided by beta square equal to 1. So this graph shows you when alpha of the time divided by b square equal to 1, then you can find this graph. If you have different number, then you use this graph. Okay, so this tell you it is like you have different if you like different, I think, surface, and then you cut it into half, like onion. Yeah, if you cut in the onion, and then this one is when your alpha t divided by b square equal to 1 on at 1. This is if this number equal to 0.6 and so on. So what does it means? That means if you have your alpha t divided by b square is you getting lower, which is you have low thermal conductivity, that means your surface of slab would be very hot, but it would take a long time for them to increase to that size. Yeah, so this is the heating of the slab. Okay, another one. So let's say if you want to know, if you calculate, for example, after maybe several seconds, after 10 seconds, what is the temperature of the center of the slab? Is it increasing, or is it can be it reach into your T1? You can calculate it from this graph. Okay. Another one for the cylinder is also the same. This is the axis of the cylinder. So for the cylinder, that's also the same. So if either it is in the surface of the cylinder or in the axis of the cylinder with the same, but then you have the graph for alpha t over r square, but not the b, but with the radius. This one is also the same. I will give you an example later on in the slides. This is also the sphere, bola, yeah. So for the sphere also the same, but with slightly different direction. But anyway, so if you want to do unsteady state heat transfer using, and then you let's say solve the problem using MATLAB or using FlexPDA, the curve would be similar like this one, yeah. Okay. Now, this is also unsteady heat conduction in solid. For example, if you have a cooling sphere in contact with well-stirred fluid, for example, this is you have an insulated tank, you have a fluid temperature T0, and then you have a temperature T1, and then suddenly you put it into, for example, you have a hot ball, and then you put it into cold water. What is the temperature of this ball, for example? This is also the same using theta as the dimensional variable for temperature as a function of position. This is for position, and also this is for the temperature, function of radial coordinate and time, this one. And then you end up with equation and boundary condition. You can have a look later on. And anyway, the result would be something like this. So this shows the variation of fluid temperature with time of a sphere radius temperature at T1 place at well-stirred fluid. So, but anyway, because yeah, this is a paper, a very old paper, conduction, heat, and solid. So chemical engineers can use this as a approach to even use this graph. So they just use this graph to calculate the this one, yeah. And then this is also there is a dimensionless parameter that shows the yeah, the difference of the temperature. Okay, now last one for this case. So this is an example a few years ago, but still in Indonesian, yeah. So let's say we have a bakso sapi, or the meatball, okay, and then the meatball is in uh, a sphere, so we can make it a sphere. In chemical engineering, I was taught that we can idealize any object into a sphere, a cylinder, or a slab. If the object is not really a sphere, it's not really slab, that's okay. But we can make a factor. For example, I remember that almarhum Pak Bubiar said that with transfer phenomena, you can detect if you find a body, jenazah, yeah, a dead body, you can calculate how long he or she has died by measuring the temperature, because the outside of the body would be cool, very cold to the room temperature, but the inside of the temperature of the body is still warm. So you can calculate the time that the person has disease. So that's an example, and it is used for the forensic as well. Right. Okay. So go back to the example. So we have a bakso mentah, yeah, or the meatball. It is a sphere, bola sempurna. Okay, the diameter is 30 millimeter. So I would write 30 millimeter. So then that means your radius would be half of it. Okay, or maybe put it like that. And then it was put in the fridge. The temperature is at 10 degrees Celsius. So maybe the T0, the initial temperature would be 10 degrees Celsius. Okay, and then it is boiled in a hot water, in a boiled water, 95 degrees Celsius. So let's say put into suddenly into a temperature of 95. Okay, and then there is a thermal diffusivity, or the heat diffusivity, that this one is about the alpha. So then you can say that your alpha is 9 millimeter square per minute. Because this is millimeters, then I would stick the R with this one as well. Okay, and then you can have a nice sketch, and then you can find the coordinate, maybe in here with the R, only the R. And then with the figure, perkirakan the temperature of the meatball on the radial of 8.5 millimeters after it boiled for 2.5 meter. Okay, so this one. So for number C, so at R equal to 8.5, and then your temperature is 2.5, find temperature. Find the temperature of that one. So because the temperature is a function of the R, and also the time. Okay, so let's have a look. Number 3 first. Okay, so here, so this is the curve. Yeah, so we can start, so you have your T0, which is 10 degrees Celsius. We have T1, which is 85 degrees Celsius. 19.5. Yeah. And then we have R, which is 85, this one, yeah. 8.5. And we have R as well, which is, the R is 15, I guess. Okay. So we can first calculate the position, and also we know the alpha. We know the alpha. Alpha is 9, yeah. 9 millimeter square per minute. Okay, so first what we can do, we can calculate the alpha T over R square. Alpha T over R square, which is 9, multiply with time. The time is 2.5, yeah. The time is 2.5. 2.5 divided by R square, which is 15 square. Anyone would like to help? 9.2 multiplied 2.5 divided by 15 square. Or maybe look at over here. This one, yeah. 0.1. Okay. So because your parameter sigma t, alpha t over R square is 0.1, then we can use this curve. Yeah, we can use this curve. Okay. And then the next one, we can calculate the position. The position is R divided by R, which is 8.5 divided by 15. Yeah, so we can check over here. So 0.56. Yeah, 0.56, 0.566. So maybe 0.56, or maybe because it's very small, so over here, so maybe about, sorry, this is number 1. Maybe around 0.56. 0.50, 0.5, maybe 56, maybe around here. Yeah. Okay, so then, so this is your so this is when 0.56. So this number will correlate into that value. Yeah. So then this value shows that, so this one, so your T minus T0 over T1 minus T0 equal to 0.5, 0.4, 0.5, maybe 0.57, yeah, let's say. If you want to say, Bu, for example, in this case, Bu, I want to make around something like this one. Yeah, I think this one is also acceptable as well, because they put different a little bit of approximation. But if you want to be more detailed, like me, like this one, because slightly difference over here, a little bit there, that would be okay as well. So during the exam, I want to I always want to check the graph also, and also check your calculation. So use nice ruler or something, and then so we know where do you get the value. So here, from here you can say that t minus t0 over t1 minus t0 is equal to 0.57, or t minus 10 would be 0.57 multiply with the difference is 85, yeah, plus 10 degree. So maybe about 10 degree plus this value, yeah, and then you can get the result. In this case, you will get that about 61%. But if you want to have a 57 multiplied with 85, that's also the same as well. It would be acceptable. So maybe around 59 to 61 degrees Celsius. So that means you can know your position of your bakso, yeah, after only 2 minutes. So don't take it first after 2 minutes, because it's still not that warm. Okay, is it understandable? Yeah. Okay. So this one, I think Madaya and also and I think you got this, Evan, yeah, you got this kind of exam, I think last year. But so this exam is actually, it's not that really mathematical, but we need to know to read the graph. Okay, so if you know the graph, you know the concept. Even for the sphere, for the slab, or for cylinder, there's also okay, that's acceptable. Yeah. And now it's number the D, point D. So if the bakso dianggap matang sempurna, so if the meatball are okay, if the temperature of the center pusat bakso mencapai 80 degrees Celsius. So how much you need to boil the bakso or the meatball so it can be okay, and then you can finish the job. Okay, so if in this case, any idea what should we do? What's the clue? So what is the temperature pusat bakso? So for this case, so then your temperature, if your known, is 80 degrees Celsius. So your keyword now is to find the in the center should be 80 degrees Celsius, and then you can find the temperature. So it's different. You know, now you will know the axis, T, the delta T, or the temperature of dimensionless, and then you find the graph. Okay, so here, so the temperature pusat bakso, or the centered temperature. So it should be, if you go back here, is on the center of the sphere. So this one. So you need to find the center of the sphere, this one. And then you also know the position, of course, the position is this one. And then you can find which graph you should find. Okay, so in this case, calculate the t minus t0 divided by t1 minus t0, 80 minus 10 divided by 95 minus 10, and then you got around 0.82 this case. So, and at R to R equal to 0, so on the center. And then let's find it, 0.82. So 0.82, this one, 0.7, 0.8, 0.9. So 0.82 maybe around this one. Okay, so it is somewhere between alpha t divided by r squared 0.4 and also 0.2. So you can make interpolation because it's roughly half of it. Maybe you can make something like interpolation like that one, just roughly, yeah. Maybe this one you can check at alpha t divided by r squared, roughly about 0.3. How do we do the interpolation, Bu? This is your judgment. This is your engineering judgment. Because it's roughly a little bit almost half, yeah. This one from the 0. Yeah, almost half, maybe around 0.3, somewhere between 0.4 and 0.1, 0.2 and 0.4. Okay, so maybe around 0.3 in this case. Okay, so because you know 0.3, yeah, this one between 0.2 and 0.4, and then you can calculate the what by r square equal to 0.3, and then you know this is 9, and this is your r square is 15 square, and then you can get your temperature. So it's about 7.5. So the meatball will be okay with be fully cooked after 7.5 minutes. Okay. So then that's why I said to you that I would imagine if I cook my chicken for a roast chicken, I can calculate how much should I wait inside the oven, for example, to make sure that everything is fully cooked. Yeah. All right. I think that conclude the topics. If you have any question. Can you check on the next? Do we have uh the slides? Do we have the slide ready in the next?
Well, is it specifically for unsteady state?
Yeah, only for unsteady state because it is only function of temperature. If not, then let me distribute this one first to you.
I don't think there's.
There's no in EduNext. All right. So let me put it into the Zoom. Just to the, so you can have a look. I think this is just because everyone hasn't really informed, maybe because last year we put some cases about this one, but no one could really answer. Wait. Temperature distribution. Okay, let me add it first before we continue to the next one. Okay. Right, this is the end of recording.